All right, welcome to our last lesson for Unit 1, Lesson 11, Emission Spectroscopy. It's always a hard word for me to say, which sounds really complicated, but it's actually very straightforward. Just the words are fancy. So we're going to be learning about the concepts of emission spectroscopy. And emission spectroscopy is, well, it's going to be involving fireworks in some way. We can see them on here. We're going to talk about atomic structure again. It's been a while since we looked closely at atomic structure, and we'll look at a couple examples. So first of all, here's an example of a flame test, kind of like what we did, though this is set up in a different lab that can have this kind of fire going at the same time. Emission is the fancy word just for the production and discharge of something, right? And this is just creating and releasing things. So, one way to think of it is you emit sweat when you're sweating, right? You produce it and get rid of it. It goes onto your body. These flames are emitting light. They are creating and releasing light into the room, which is why you can see the different colors. So spectroscopy is the study of the absorption and emission of light and other radiation by matter. And to say that simply, that's the study of how objects absorb and give off light, like why my shirt is currently white, why my wristband is black, why these flames are all different colors, and how that's related to chemistry. That's what we're studying with spectroscopy. Now, therefore, the emission spectroscopy is the study of how matter emits light. Why the stuff we look at is the colors of light that we see, or the kind of light that we see. Okay? And we're focusing on chemical emission spectroscopy, obviously, in our chemistry. So here's one way to look at this. This is the Dalton model. Again, right, this is this flat 2D model of an atom. It's not perfect. Models never are. But it's a way for us to really easily see electron orbits and how all these things interact. The center of an atom, remember, is the nucleus. In plural, we say nuclei. And it has protons, which are these positively charged particles, positive just like on a magnet. And there's neutrons, which are neutral particles that don't have a charge. Okay, orbiting that center is electrons. These are negatively charged particles in distinct orbits. They have distinct spots they hang out in. They can hang out just anywhere. You can see it shown here as these circles. Now, electrons can be lost to or gained from other atoms. Atoms can share or pass around electrons. When an atom has an unequal number of protons to electrons, it becomes an ion. An ion is just any atom that is not balanced, so it has a magnetic or electric charge. Okay? It's positive when there's not enough electrons to cancel the protons, or it's negative when there's more electrons than protons. Now, the metal ions in our lab all had an extra electron from the chloride they were paired with when they're made into salts. Lots of salts are made with chloride, just like the salt on your table being sodium chloride. Now, when we heated these metal ions in the flame, they gained energy. And if you see this example here where we have a kind of an Dalton model with none of the protons or nuclei or electrons except for one, these orbits have specific amounts of energy they're associated with. The electron takes a full step, like a staircase. You can't walk half a foot or 3 feet per stair. You walk whatever the stair is set up to be. Okay? And we have a little GIF here that shows what happens when they absorb the exact amount of energy to jump up. They'll jump up like you see here in this little GIF. Okay? Now, eventually, because that's not where the electron normally sits, it's going to come back down. There are forces in the nucleus, kind of like the forces of gravity, right, that keep pulling it in, pulling it down. And so, just like if you jump up, gravity pulls you back down. Eventually, this electron will get pulled back down, and when it does, it has to let go of the extra energy. And that extra energy gets pushed off, just like you see here. And what's interesting about it is that light of different colors has different energy levels. Red and green and blue light is all different amounts of energy. So when that electron falls, the amount of energy that gets released is unique based off what element we're looking at. So all the different elements that we're talking about, they have different amounts of energy released when this happens, like burning or just shining light on them. That's why elements are different colors when you put lights on them. Now, each metal ion has a unique color, though some colors might be so close that it's really hard to tell with your eye, like that's purple, that's red, that's red, that's green, that's green. But the actual greens, the actual reds, the actual purples could be a little different. But when you're just looking at a flame, it can be really hard to tell which one's light purple and which one's lighter purple. So here's a question to think about. Why do you think the video started with a picture of fireworks? Take a moment, maybe pause, think about it for a second. If you guessed that those fireworks that you see at Disneyland or anywhere else, the ones in front of your house, the colors in it come from these metal salts or other elemental particles that are then heated up and then release light in those colors, that's actually correct. Understanding this kind of chemistry is what we had to do to make fireworks. All right? That's it for our lesson and for our unit. Good luck on the project, and I'll see you next time.